you very much for coming. My name is Andrew Gakov. I work for Ferret Go GmbH. This is a company, a German company. We are right now, we are a small company, but right now we are leading company in community moderation and analytics in Germany. This talk would be, I think it would be different from other talk which you maybe listened today or yesterday in this conference, because I will not talk about any products. I will not advertise any products. I will not say how I fail in this. I just want to give you some hints and some, let's say, some educational inputs which you might be used in your everyday, let's say, developers' lives. And today I want to talk about time series. Of course, time series, that's a huge topic, and we cannot cover everything today. But so today I will just say, let's say, some basic things, and I will show you tools, Python tools, and examples how you can apply these tools to the time series. But first, we have to answer the question: what is the time series for us today? So today we will say time series is a sequential set of data points measured over the time. So this is the only what you need to know about time series right now. It's sequential and it's over the time. And the time itself has really, let's say, bad feature. Yeah, it always goes forward, and you cannot go it back. And this is why analysis of time series, analysis of data which relates to time, it's different from other analysis, and sometimes it's hard. But first, let's look at examples. What are everyday applications of time series you might see in your company? So, for instance, number of page views could be modeled as a time series. For instance, temperature in your city can be measured as time series. Some income for the company, some population data. And all this data you want to analyze, of course, and what is more important, you want to predict. For instance, from the previous talk, we say they have, like in Data Robot, they have some prediction about the usage of resources. This is also the application for time series analysis. Of course, there are many tools, and we will talk today about them, but first we need to understand the basics. So what is time series and what you can get out of time series? So time series can contain many, a lot of information. So for instance, you can get out of time series a general tendency in the data. You can get some seasonal effects. You can get some occasional events. So a lot of stuff, and we need to know how to, let's say, decompose the time series to get this data. And this is why we start talking about time series decomposition. So first, and maybe that's the most known and most natural things what you can get from your data, that's a trend. Trend, that's just overall tendency in your data. Yeah, this is something which, if you look on the visualization, you will always say, is it growing up? Is it growing down? Maybe it's some growing up and then growing down, or something like this. For instance, this is a real data set from World Bank about the cost of gold. You can see there is a tendency in this data, right? So it can change, it can go down, it can go up, but the tendency is growing. Yeah? So this is the overall tendency, and maybe if you are here and you want to invest in gold, that's not so bad to invest. But if you are here and then you don't know the tendency, that for you what could be a big, let's say, a problem. Gold is growing down, and you don't know what to do. Should I invest or not? And if you know the tendency, it's okay. You can buy in this point and be a little bit richer than a few years ago. Okay, the second part, what we can get from the time series, this is a seasonal components, so seasonal effects. So they are periodic, and usually we are talking about them in the scope of 1 year. So that's, of course, you can say you have a seasonal like every week and so on, but usually this is about the yearly seasonality. Yesterday, I think that was there was a presentation about Evo was launching new design, and they says, okay, how to efficiently compare is our new design works well or not, and they just open Google Analytics and see, okay, this March we get, after we launch new design, we get more visitors than last year at the same time. Of course, this is true if you have no trend. This is why you have to not just compare the data, but you also should compare the seasonal effect, which was done really good, because in March maybe more visitors than in January. But also you should consider a trend. And this is how seasonality looks like on the visualization. So this is the temperature in my city, Berlin. You see every year, for some reason, it's cold in winter, and sometimes it's hot in summer, right? And you can see there is no trend right now here. Yeah? So, of course, we always say, yeah, it's getting warmer and warmer, but if you take the visualization, you look, okay, this is just a normal fluctuations. Of course, it's sometimes colder in April, and this year it was really hot in April, 28 degrees, for instance. It happens because there is something more in the data, not just trend and seasonality. Oh, that's not that one. Not so perfect. Okay, there are some cyclical effects. So this is not like seasonal effects, which is let's say continue again and again and again. But this is something which you can see in really long terms. For instance, if you know in economy there is a Kondratiev waves. Yeah, so they again and again after, I don't know, 30 years happens, yeah? So it's really hard if you see just a part to get them. But if you know, it will improve your, let's say, way to predict the data. Just an example, this is monthly reported number of cases of measles, kor, болезнь. Which is popular now in Ukraine, I know. So some periods of time, so usually in scientific literature you can find what the measles comes again and again after 5 years, about 5 years. And it stays for about 1-2 years, and then it changes. So here you see just what it happens again and again in the scope about the 5 years. But of course, this is not periodical. So you cannot say, like, in 5 years we will see you again. No, maybe in 4 years. And if you will not make a vaccination, you will see them much earlier. Okay, and then of course, something which we don't know, something like a noise, something like, I don't know, revolution. Yeah? Something which makes your data really unpredictable. We are lucky because these effects, they are not really often, because if they will be often, then we can really predict them. Yeah? If they say that, to us on TV, on somewhere, say, okay, every Monday we will have a new government, then we can predict this data. But if government comes like unexpectedly with some, let's say, political fluctuations, then it's a problem. And as an example, I look for example, what kind of irregular examples we can find. And again, this is daily average of a currency exchange between euro and hryvnia in 2014, which was famous year. And you can see there are two irregulars. So there is a trend, of course, as usually euro is growing, hryvnia is going down, but there were two peaks. So this was February, this was the revolution part, and that was the military, so the war starts, or how it's called right now, I don't know. Okay, so it's hard to predict. This is a force majeure. Yeah? This is effects which You can try to model, but in general, you can say that's residuals. This is something which we cannot really predict. And this is why, because such residuals, they could be a lot. And this is why in time series, you cannot really be 100% accuracy. You can't get 100% accuracy. And usually if you get 70%, that's already quite good. And this is why you should not believe, let's say like this, what you can take Bitcoin price for last year and try to predict this for the next year. I mean, of course, if there is a trend, but there is no trend, I just spoiler you. If there is a trend, then you can at least understand will you be in profit or not. But in general, you cannot really get because there are, so the effects of these residuals, which are not seasonal, which is not trend, they are quite high in the Bitcoin price. In general, it's called, in general currency, it's volatile. Oh, come on. Okay, so, but now we know what we can take this data, look on it, and then we can split by trend, seasonality, some cyclical effects, and some noise, which we can say. But now, if you want to model something, you want to merge this again, right? So to say this is a model of my time series. There are two main models, and one of this that's just additive. Then you can say, you say, okay, my trend is not related to my seasons. My trend, just a generic tendency, it just grows up, and seasons, they are not changes at all. So for instance, you can say if there is a warming, let's say global warming, and some seasonal effects like, I don't know, my temperature in June is 20 degrees, and in January is 10 degrees, they are not related too much, yeah? So it will not be like, if warming is a little bit more, let's say plus 1 degree, and then temperature in January would be 15 plus 15 or plus 20 degrees. So it will be still in some periods, so they will not really related to each other. And just to see an example, so okay, you can see this visually on the graph, and let's look. Okay. Okay. So how to see this? So if you look on the graph, you just don't see what with trend fluctuations of seasonality, not increases. So fluctuation of seasonality on the graph just normally from year to year does not matter is it growing or it going down, the trend. So this is how you can see on the graph. We will see this on example. Another one you can say, okay, all of them dependent. So if trend is growing, this is why this is also say what our seasonality is also growing and fluctuation becomes bigger and bigger. You can also see this on the graph. Let me show it. This one. So you see this is sales of alcoholic drinks in UK. You see, this is a global trend, let's say like this, so it's growing up, and then at some point they decided not to sell too much. I don't know, maybe nobody drinks. Okay, but you can see this is these two components. You can see here trend and seasonality, and trend is growing up, seasonality doesn't change. And it's growing down, does not change too much. It always, let's say, in the same interval. But if we look on another picture, this is number of airline passengers. So you see the number of passengers, overall number of passengers, it's growing up, but it's growing up and also seasonality growing up. Yeah? So that means they're related. So because every season, let's say, more and more people going up, for instance, this is why trend is going up. So this is definitely a multiplicative model, and this is an additive model. Why I let's say stop too much on these small details, because this is actually half of analysis. So if you can detect which decomposition model you can apply to your time series, that's already half work done. And I will show you how to make it. And for now, let's look on demo. So I take just a real-time data set, and with Python tools, I use Jupyter Notebook for this case. And you can see this is a number of visits to UK all passengers from foreign countries, and the data set looks like just a year, a month, which first of the month, and then it's just number of passengers in thousands. Nothing special, and we can see if I visualize the data. Okay, so how it looks like. So there is some trend, and we see seasonality, and which kind of model we can apply? Is it additive or multiplicative? Additive, I also think so. And I will show you why it's important a little bit after. But first, let's look on the data. So if we look on the trend, let's say trend, you can think about trend if you take a moving average. So just a mean of the data and see how it changes during the time. And it will go something like this. And you see here and there are 2 points where something changes. I ask Google, how it's, okay, Google. No, okay. This problem, it was in 2001. That was after the terroristic attack in US, because US visitors was a bigger part of the visitors to UK, which is natural and we can expect. And right, and then in 2009, so it started growing up again and again. And then in 2009 was the financial crisis. Again, US was not really happy in this place, and again the number of passenger drops, and this is two main points. Of course, I check also what kind of who actually visits the UK. Usually it's the US, Germans, and French people. Okay, great. So if we a little bit zoom, we can see what there is seasonality, which is almost perfect seasonality. So people usually at summer go to UK and less in winter. And also I check in Google. Okay, and the question was actually what is the best time to visit? And the best time to visit, they think that's a late March and early June. But we can see what that's not really true. This state was from the travel agency, which say, okay, you should go to UK and this. Okay. So this is the data, quite easy. And now what we can do, we can try to extract the trend, seasonality, and some residuals, some rest of the what can be in the data. And this is where the importance of which model it is. And we can see there is, I will use the additive model, I will use StatsModel package. I will tell about this package a little bit later. And I see what there is a seasonality, and it's perfect yearly seasonality. So this is good, and this is why I say that's a 12-month seasonality here. And then I just use decomposition model. Nothing special, I don't say about Teferi right now, but what you can get immediately, you can get your trend. This is your trend. And now if you want to, let's say, build a trigger in your application, which will notify you when your number of visitors to your websites dropped. Yeah? How you know? You need some baseline. You can use this baseline as the trend as your baseline. So if it's less than values on your baseline, that means that something should be triggered and somebody should be called and should take a look in this data and say, is it normal or not? But again, based on some other models. But this is something good, like to fast triggers, to have a fast triggers. Then we can also get the seasonality effects. You can see it's almost perfect trigonometric function. There are different values here, but it's not visible on this graph. So looks like that. So also good. So that means it's. Then you get something like this. That means your trend separation was almost good, almost perfect. Okay, and there are some residuals, some noise, which we don't know. It didn't come from seasonality, it didn't come from the trend, but maybe it comes from some other effects. And of course, you can understand what there are many more effects what can change the data. I don't know, some conferences Olympic Games, and so on. Let's back to our data. So now we know how to analyze the data, so how to look inside the data. But what we want to do, usually with time, we want to predict the future, right? But before we predict the future, we need to understand how we'll measure what we will get. So how we'll say what this prediction is good and that prediction is bad. Okay, so there are a few, let's say, there are many metrics, but let's look on a few of them. The easiest one, this is just a mean, so you take your prediction, you take your, you take your data and see the difference. Of course, that's not perfect because you can have something with something up, so something like overestimation, something underestimation, and then in some they will compensate, make compensation on each other. But it's really good to see the direction. So are you overfitting, are you underfitting, and all that stuff. So you can improve, it's not perfect, and you can improve, you can take the square. Then there is no problem about this over and under fitting, but still it's not good because if you have such, let's say, some anomaly in the data, it will make your metric really unuseful. And this is why you can normalize it by the variance, and that's already quite good estimation. But again, if your values x here, these values and these values, they're quite big, the sum could be also really big, and you can have just a computational problems, for instance. This is why you can have another one. Can you? Yeah. It's called Telius U statistics. That's just a norm, normalized in different way, let's say like that. Quite useful, and the important part here, it's always from 0 to 1, at least you can really interpret it quite easy. And just one more, you can look this, you don't need to remember. I'm just show what you can find. And there is a R-squared coefficient, which this is a measure of variance in your data. So it just say, let's say, in how much or which amount, let's say, of variance you predicted well. So if it's equals to 1, that means it's you predicted everything, but you never get it 1, and this is why values from, I know, 70%, so 0.7 to 0.9 is quite good values. Okay, so we have this number of measures. You can find them a lot. If you go to any statistics website or read a book about this, you can find, I don't know, maybe 100 of them. They have different application areas. And as soon as now we know how to let's say, look inside the data, we know how to measure our let's say, prediction, and now finally, models. So how we can model the future. There are, let's say, 3 big classes of models, which we will maybe talk today. But first one, it's most known. That's the stochastic models. Stochastics mean there is some probabilistic process inside the data. So let's say you assume that there is some probabilistic process inside data. And most known and the easiest one, which already, I don't know, 70 years, I think, for this model, this is ARMA. It's called After-Regressive Integrated Moving Average model. So this model just assumes what your data has a special property. This special property calls stationarity. So let's say your process is stationary. That means there is no trend, no seasonality. It's just no, let's say, functional dependency inside the data. This is really unuseful, let's say, unuseful assumption, but we can build on top of this model another models which will use this model as a really good core component in the data. Okay, first, if you want to use such class of models like ARMA or its modifications, you have to somehow to test, is your data actually fits to your model? Let's say, is it stationary or not? There are some tests what you can apply, and I will show you how to do this. There are libraries, you can use it, no problems. But again, it should be stationary. Yeah? Why it's called ARMA? It's from acronyms R and MA. It's two processes. R, it's autoregression process. Let's say, you can think about it as a long-term process, so it remembers a little bit like wide intervals, and you have a moving average process, which is responsible to the short intervals. Of course, you can, if you look in the data and you naturally think, okay, maybe for values today, tomorrow, important values today and some years ago, right? So maybe Bitcoin price tomorrow will rise because something happens today, or something happens also like a week ago. And this is why it's naturally what you want to have two processes to look, to remember what happens like recently and what happens long time ago. And this idea comes to ARMA, and this is why it's these two processes, R and MA, was used there. And it has two parameters, one for long, so how many legs you want for a long process and how many legs you want for a short process. Okay, but it's not really useful in business application. This is why there is a modification. It's called ARIMA. ARIMA, it's a ARMA plus integrated time series. Integrated time series means what the time series what you have can be converted to the stationary time series. 90% of your business applications can be applied to ARIMA, because you always can remove the trend, you always can remove the seasonality, and then you can get this ugly but good condition data to apply ARIMA. ARMA. But the problem, still, there is a problem here, because ARIMA can handle the trend, but not the seasonality. And of course, we know what our data, most of our data, they have seasonal effects. Yeah, you know, on Christmas, people buy much more than, I don't know, in June. There is one more parameter here. This is, so if you convert your data, you have another parameter in how many steps you actually converted it. And then if you know these three parameters, you can apply the model. But again, if you want seasonality, then you cannot use ARIMA directly, and you have to build another one, which is called SARIMA. SARIMA, okay, surprise, surprise, it's seasonal, autoregressive integrated moving average, and it just has another process for your seasonality. So it's ARIMA plus additional process which will model your seasonality. So what you have to do if you want to apply these stochastic models. So first you should check your data and see if there is a trend or not, if there is a seasonality or not, if it's seasonality and trend, you use SARIMA. If it's only trend, then you use ARIMA. If nothing, then you use ARMA. Nothing special. And to do this in Python, you can use really nice and really powerful library. It's called StatsModels. It's quite old. It's quite old package, but it has everything what you need if you want to work with statistics. And in this package, it's almost straightforward how to do this. As soon as you know the parameters of the model, you can just call SARIMAX. SARIMAX, that's another one, another modification of SARIMA. In mathematics, you know, in mathematics, there are thousands of modifications, and you have to know which modifications to use and when. And that's a problem. This is why you need a mathematician in your company, by the way. Okay, so you just build a model, and then you just fit a model normally, as usually we do with not time-dependent values. And then you can get some forecast, so how many steps, that means how many, if your data is let's say, monthly data, then how many months in the future you want to predict. And then also you can have some confidence interval, so there is a prediction, but there are some, let's say, fluctuations, what might be, and you should understand what the prediction is just, let's say, average from the model, but in general it can jump out, I don't know, to 10%, for instance, and you have to be prepared for that. And then you just get the predicted values, and you can compare these values. Really easy. Of course. So let's look on example. So I already get data into the Python notebook. This is the same, our same data. I split data to testing and validation, let's say train and testing data. There is no validation because validation will be done inside the model. And I apply the ARIMA or SARIMA model. So first, what I said, you cannot just take quick start manual and apply this model. It won't work because you need to know the parameters, and you can get parameters only if you, let's say, normalize and prepare your data to be useful or can be used by the model. And first, what you have to know, you need to answer your question: is it stationary or not? So you need to make a test, and one of these tests, this is augmented Dickley-Fuller test, for instance, or Kwiatkowski-Phillips-Schmidt chain. It's KPSS. Let's look on KPSS. It's known for some areas. So you just apply these tests. You can import them from the StatsModel package. They're available. You don't need to write any scientific code at this point. You can apply, and then you see here, for instance, it says no and no. They are quite different, these tests. This is why usually you have to apply two tests, two different tests to be sure what you are not wrong on your test, because every test, that's a statistical test. It has error, and sometimes error can play a really important way. So, and here we see it's not stationary. So what we can do so we can make a special procedure. It's called stationarization. I don't want to be to stop on these techniques, but for instance, one of them, it's called first difference. So you can just make a difference between your time series and your time series shifted by some number of legs. That would be, in most cases, enough for you. And if it's not enough, you can make it again with the resultant. And then how many steps you get, this would be your parameter for your ARIMA model. So I did some tests. And then, so I did some changes for standardization. And then at the end, what I get all of them actually stationary now. So I removed trend, I removed this seasonality, and it now looks like that. Usually stationary time series is something like a noise, but it's not a noise. But looks like a noise. White noise, that's... Okay, then the hard part, which I don't want to stay, so how to get now parameters for ARIMA. You can read these Python notebooks, they're all available in GitHub. You can look on them and try them, everything works, I hope. But you have to find these parameters R and MA. And for this purpose, you have to use, it's called partial autocorrelation function and autocorrelation function. So again, that's a mathematics, and you don't want to know this. But what you need to know, as soon as you apply them, there are such a number of legs which has a majority, call it like majority on the graph, and that would be your parameters, which in my case, 1 and 1. So only one leg, and here is important. So if you want to have the idea what it means, you can say how many legs or how many steps in the past we should go to get enough information for this time series. So how far in the past all necessary information is encoded into the data. And then we know the parameters, we get this 1, 1, 1 from the autocorrelation and partial autocorrelation function, and we use the same parameters for, this is a component for seasonality. You see it's yearly seasonality, so 12 months. And I can apply the model and make a prediction. So this is my prediction here. I don't want to zoom because now it looks almost perfect, but if you zoom, you will see it's not like that. But it's quite good, actually, for this data. Also, you can notice what the far you predict, the more error you get, right? So this is why you always should think why it happens. So first, why it happens? Because your error accumulates. So every time you predict more and more and more, it remembers the error because it cannot fix itself, right? So and then if you have error here, I don't know, 1%, but because of this error, this one will grow. You have error in trend, you have error in seasonality, and of course you have error in noise, which is this is why you should, if you predict, it's better to predict for short intervals, maybe a few steps, if it's monthly data, a few months in the future, but not like guys come and say, what would be the weather? Don't use time series for weather, but still, what would be the weather next year? I can tell you, it would be hot at summer and cold in winter. This is quite good prediction, and pretty sure 60% or no, 71% it will be true in days if you will compare it. Okay, you can see overall interval. This is my prediction, and this is the real data, and this is the confidence interval. You see, confidence interval, it grows up. So the uncertainty in data, it grows up, and it's far you go, it's more sure you are what will happen. And that means it might be happen what in October 2017, the data would be not here, but here, which is from 3,000 to 6,000, which is 100% difference, actually. So, okay. If you apply this measure, what we just talked about, so you can see if I predict the full test data, my measure, let's say like that's a absolute error, just a difference. You see, I'm wrong only for 126, and our data is about 3,000. So that means I don't know how much, 5%, no less. So 300, that's a 10%, so 5%, yeah? So I'm wrong for 5% only, but this is for the long test interval. But if you just look on the only 12 months ahead, just next year, you will see what, same prediction, nothing changes, same prediction, it's much better. It's already 2-point-something% error. Right? This again and again I tell you, so you should not predict the far future, or if you predict far future, you should accept what your accuracy would be not so high as you might expect. Okay, but this is the old way to do this. You have to know mathematics, you have to know how it works. Recently, Facebook just announced its library. It's called Profit. This is library for time series prediction, but they let's say they built in the model which will be good for, I know, 80% of real business cases. This is important. So you cannot apply it everywhere, but for real business cases that would be much easier. And let's say, so say like that. If it works good. If it will work good. If it doesn't work, you have to learn mathematics and apply real models. It has its own model. It's always assumed what your data is additive. This is what happens usually in business data, but that's not a problem. Mathematically, you can convert a multiplicative model to additive if you really want. And they have a little bit different modeling. So they just say, okay, trend, we always can model with a line or with exponent. And the seasonality, we always will try to model with Fourier time series. And then if it fits good, and it's in many cases it fits good, then you will be happy. And to apply it's much easier than the Sarima or Arima or all this family. You just import and predict. There are some parameters. I have no time to go deep. You can look this in my IPython notebook, which will be available already available in GitHub by this link. It's good. So let me tell you a small, let's say, short note about the profit model. Profit model is really good. Then you have a normal time series which comes from business application, which is related to, for instance, to holidays. This is really good. You can encode your holidays. Then you know why you have such points in the trend which changes your behavior. So, for instance, we launch new product, we launch new design. You can also encode in this model. Then your trend is actually growing or going down without any weird fluctuations. Then it also will work quite well. But most important stuff, what like everybody doesn't who never read about time series can come and apply this model and get the result. And then they can take the currency and then apply this model and then make a post in, I don't know, Dow. And say, yeah, I just predict the hryvnia, and you see now you can invest money. So quite good. But okay, so still this is a family which is about seeing data as a probabilistic process. But right now everybody says, okay, but why we should know mathematics? Let's apply neural network. Yeah? And I did this, so you can apply actually artificial neural network to predict time series. It's nothing. It's much easier if it works, much easier than the Sarima. You know what is artificial neural network, right? Everybody knows. So you can see it's a graph. There is some information comes from ages, and every node does some calculations. And there is a function which is called activation functions, which works in this node and make this simple calculation. So many different types of artificial networks, but there is a classical one, it's called feed-forward network, and there is another one, classical, but it has a recurrent unit inside. For long time, this network didn't work because there was a problem, gradient explosion, but recently, 10 years, even more, it was fixed. And it was fixed with a special unit or special architecture. It's called long-short-term memory. Long-short. So again, that's already something which you should think about time series. It has long and short memory, which is important for time series. But the name comes not from this. It's the name comes from the way how you forget data. So in recurrent network, if you learn data, you will get the same problem as we see in time series. You will accumulate the error. And sometimes it's better just to forget than to try to fix this error as normal neural network did. Okay, and I will use this LSTM architecture. But the problem with neural network, usually if you take the neural network and see, again, read maybe quick start manual, you will see what sometimes it works, sometimes it's, in most cases it doesn't work actually, because you need to know which parameters to use, how many steps to train, and is it actually is it my network is good, so should I use 100 input units, or should I use 5 layers, or what kind of neural network I should apply? And that's a problem, but for time series this problem was answered, and this is good. This is why we can apply the neural network for this problem. It's called SAN, Seasonal Artificial Neural Networks. And they have really good, let's say, scientifically, scientists, they found which parameters to use. And it's quite easy. You need only one hidden layer. Cool. Number of input and output neurons, so input and output of the network actually same. And then number of hidden nodes, they just say, take a few take a few and it will work. Let's look, will it work? But the problem, you cannot just apply neural network on your data, because it's like just a sequence, not enough to train usually neural network, and for neural networks you need, so neural network, nobody knows actually how it learns, right? But everybody knows what more data you have, more probability it will learn something out of data in some way. This is why we need to prepare data, and we need to feed to network some vectors and get some values out of the network. This is why what I use here, I just, for every moment of t in our time series, I just say, I will learn next season based on the previous season. Quite good assumption. I can say, I see what happens last year, and I try to predict what will be next year. Quite okay. Okay, and then I just feed this, this component, which I get xt, to the neural network, and I hope it will give me something close to our next season prediction. And if you say neural network and you say Python, you have to say keras this year. And last year, it's really cool. If you never use this Python tool, you have to definitely look. So really cool documentation, really powerful, and this is really amazing. You can use different backends. You can use Tiano. You can use TensorFlow. So really nice. And what is important, it has the interface same as scikit-learn. Scikit-learn. This is a library. What if you ever worked with data, you used scikit-learn in Python. So how it looks like, this is the network. This is how I built the network from keras. I just said there's a sequential network, so layers goes like this, one after another one. I have input layer, and as Sun seasonal artificial network says, you have to use just number of seasons as input, and then I use number of seasons as output. Here, and then I use one LSTM, so recurrent unit inside the network, and only 4 nodes I use in this. So my season 12 nodes, my hidden layer, it's called only 4 nodes, and then I have 12 nodes in output, and I just build a model, and then I just feed it and predict. Really easy, and again, you don't need to, let's say, convert your time series to a special way to get parameters. So you just actually hope what network will do this for you. But that's the reason why you use neural networks. So I want to show this example, and I have no time. Artificial neural network. So for artificial neural networks, I will split data by 3 parts, because I want to train network, but I also, let's say, validate how good it's actually training. And then I will same data to predict the future. So as I already said, I need to transform the data to convert it to sequences. This is not interesting code. And I just implement some of the metrics which I told you before. This is R² and teleosymmetric, which is implemented in tensors, call it like that. Because I cannot really use standard one. They are not ready to tensors, and keras operates tensors inside. Okay, and then I already showed you, I built this small network. So input layer, hidden layer, and dense layer. And in this case, I just took 40 epochs. So 40 epochs. If you ever work with neural networks, you know what 40 epochs, that's nothing. So that's a 40 training steps. That's really a small amount of steps, but even with these steps, you can get good results. I thought I will do a live demo, but I won't. You can see on validation what we actually, our error goes down, and we see there it actually learns something, which is a good. And after I feed the model, let's skip some code. This is what I can. I do validation. What is this? So it's about 10%, less than 10% the error, and this is R square coefficient. Remember, I said this is the amount. This is how good you predict the variance, and we predict variance with 63% accuracy for a long interval, which is quite okay. But of course, that's not a production-ready code, so don't take it and put it in production. So, but it will, at least it will work and show you. This is how prediction look like. You see, we see here it's not overfitting. That's really important because neural network can easily overfit. It can learn all your data, and that's it. And it will not learn will not predict the right data in the future. And you see, it's not overfitting. There are errors even in predicted, even in learned data. And this is our validation data, which is quite good. And this is our predicted values, which is okay, acceptable. So this is how we predict. So you see, it's not good as Sarima. It's not good as Sarima, but it's okay. It's okay to use it. Especially what I didn't use too much steps. I didn't apply special techniques to make neural network learn, let's say, more information and maybe convert in different ways. But for let's say educational purposes, that's really good fit, and you can already take it from my GitHub account and try to make it better. I did it better, I can tell. It's about 10,000 steps you need to train the model, which will take you, I don't know, on this laptop it takes, I don't know, maybe 3 hours, something a short time for neural networks. Okay, and the last one, which I will not, it wanted to be noticed. You can use support vector machines. So support vector machines, this is a special techniques which converts your data to some really high dimensional space, and in that space you can separate your data with a line, which in higher dimensional space would be hyperplane. Yeah. So you use this for classification usually, but it also can be used so-called for regression, so for prediction. There are some parameters, so you can say how strict you will be. So what is the penalty in your model? Let's not say since we have no time. But in general, to predict with support vector machines, we just take a little bit different approach than with artificial neural networks. So we just take whole season in the past and predict next month. So we have input of the past whole year and predict next month. Why? Because this model usually predicts only one value, and so the natural way to take the value to predict would be the first unknown value from the data you have. And then you can apply quite easy, and if you want to apply, you will use, of course, scikit-learn. Scikit-learn, I already told, that's a really, let's say, first library for scientific computations or for data science in Python. If you never use it, you have to just skip the lunch and go to try it, because it has amazing tools. It has everything what you need in your data science. Quite easy to apply, nothing special. It's the same interface as keras, or keras has the same interface. You just import, you just decide the parameter. You always use RBF kernel. I don't want to go deep, but that's something which you want to use, and then you just predict, and no problem. Okay, so of course it's a huge topic, and I have no time to just cover it all, but you can go and check in my account, so how it looks like, and you can try, and I have some notes more. But something what you have to do if you want to work with time series. So first, you always should visualize the data, because this is the perfect way to understand what data is. No computer program will tell you what you can really in 5 seconds get out of the data. So second, you have to understand, is it an additive or multiplicative model? So it may be weird, but additive, multiplicative, you just want to say, there is a dependent components inside or independent components inside. This is the most important. As soon as you find this, you know the decomposition model. As soon as you know the decomposition model, you can find the right model to apply the predictions. if you apply model, you should always read what about this model, because some models can only accept data from 0 to 1, so you have to scale. Some models, for some models you have to normalize. For some models you have to remove the mean. For some models you have to really transform the data, otherwise it will not work and you will not know why. Usually use, if you work with machine learning, you have to know what you have to use training data and test data. And for time series, because you cannot shuffle the data, in time series you split data and take your test data after the end. And after you train the model, you already know the result, you think it's perfect, and you just want to show you for your report, then you apply it for test data. Because otherwise, you will just use your test data as train. If you will see result, oh, it's bad, let's change some parameters. So it will not work like that. And that's the difference from the normal machine learning approaches. Then you can shuffle again the data. And this is what's written here. So don't shuffle, and time always run forwards and never go backwards. You cannot just split this. Thank you. Thank you very much.